The verification fails to keep up. Design complexity may be growing faster than the verification tools and methodologies are evolving. This is resulting in increased delays for chip success. Experts at the table, semiconductor industry sat down to discuss the state functional verification with Mohan Dene, Director of Technical for Architecture and Design at Alphawave Semi, Andy Nightingale, the Vice President for Product Management and Marketing at Arteris, Dinesh Rao, Senior Group Director for Software Engineering Cadence, Chris Smith is a new opportunities business venture site, and Gordon Allen, Director of the Verification I Product at Siemens EDA, and Frank Schirmeister, Executive Director for Strategic Programs and System Solution and Synopsys. What follows exerts data discussion. DSC. For many years, ASIC verification has kept up with the increasing design complexity, as indicated by the first-time success numbers coming from the Siemens Wilson Research Study result. New tools and methodologies contribute, but the last couple of surveys, see Figure 1, have shown in this relationship has broke down. As more chips are failing, what is going on that's making the verification more difficult today than it was just 2 years ago? Figure 1 is the first past success rate, source Siemens EDA and Wilson Research. Nightingale. Exploding SoC complexity is one thing that we keep seeing and writing about, and we've gotten dozens of heterogeneous compute elements in this every design, and more recently tied to the connection with the chiplet. What we are seeing is that this rising complexity is not being matched by the complexity of the verification IP that goes around that. That is a big challenge for the entire industry, and we needed a deep component for the individual element to expand to the system level. Everywhere there is a protocol change, or everywhere there is a die link, that's where we get challenges. We are seeing the customer design with thousands of interconnect with 1,000 of initiators target devices. All of these are packaged up as individual elements that arrive as goods into the customer, and they unpack the individual test benches. They run those test benches, and maybe everything reports, okay, the heartbreak is fine and green, good coverage. And they are plugged into something else that there is an issue. They found a corner case that they have previously anticipated. Maybe things may happen in a different order, and we have to try and find the root cause and fix it. The complexity issues is going up and up. Complexity is growing exponentially. You can graph it with Moore's law, the numbers of specs and the data speed. However you want to do it, it's growing very quickly. The problem with exponential growth is that it's easy to miss something. All you have to do is miss one thing within the exponential bubble, and your design fails when you have a lot of interdependent physics and interdependent specs, or an electrical spec affecting another. If we missed just one thing, or one noise that developed somewhere along the line you have not anticipated, haven't thought of, the integration will kill you. Then, so it is not just the first pass silicon. The failure rates are going up, and but the project timelines are being impacted too. The main reason is design complexity, but logic is being packed in these days. For the first time, hardware is not able to catch up with the software requirement, and the data gap is increasing. Secondly, everybody is doing more chips. Earlier, a company would probably do one chip every 1 to 2 years. Now we are seeing the rate growing of maybe 2 times or 3 times more chips in the same time period. But engineering resources are growing and not scaling up that fashion. And finally, we see the specs constantly evolving because of the dynamic nature of the design cycle. Any changes in the spec result in a lot of downstream challenges. For example, a simple change in design has to be worked into coverage and so on. These are really contributing to challenges in the first pass success rate. Since the start of the AI boom, and we have seen an increasing number of workloads that need to be run, if you really want to see a behavior, you don't have a way to run system-level test cases before test out. And the best way to running those is having silicon. The fastest way using a traditional simulation methodology, which started with architecture exploration, followed by RTL simulations, followed by level simulation, and the post validation. And this cycle needs to incorporate a mixed model because the complexity is increasing. At the same time, there are different workloads we need to run. As the spec continue to evolve, one change in the spec or one wrong identification of a feature or less understanding of the feature and the spec becomes a bug that are not thought of. We see more designs that are almost at the electrical size limit, which means that we are seeing the more chiplet. That means that multiple dies talking to each other, and they are executing their own workloads with or those workloads simultaneously processing their own work. It's very difficult, extremely difficult to have an environment that can identify flow in this model. That we are missing today, and that is where we should focus going forward, especially with workloads which are exponentially getting more complex. Sure, Meister. Verify here to 4 components, and they all have been mentioned with one exception. First, software complexity. Depending on the application domain, you look at the cost going into software. Software is increasing in automotive by the factor of 6 times. Hardware complexity is second. For hardware complexity, we need to be more differentiated because verification happens in phases. IP, subsystems, chip, SoC, chiplet, and multi-die within the system. Hardware complexity is now the 2 orders of magnitude or even the 3 orders of the magnitude more complex than just a couple of years ago. The other 2 elements are interfaces. In terms of interfaces between specs and different interfaces, and the last one is the one that hasn't been mentioned yet. Together with the workload execution, there is a situation that we are simply getting much more architectural and clever. If you look into the architecture space for those workload optimized systems, I'm still digesting whether the hardware really doesn't catch up with the software. Workload optimization architectures make it a lot more complicated because you have an architecture space that have many configurations of the interconnect, many options for computing, many options for accelerations, and many options for interface of the various generations. This is like an m times n times k space to explore and verify, which becomes really difficult because it's possible now to do all those options, in some cases financially relevant to do so alone, as well as all exponential curves that we all agree on. There is a cyclical effort in innovation and economic cycles. I hesitate to guess how long the cycle is. Maybe it's 15 years in some cases, or 5 years in other cases. We are seeing the perfect confluence of events on the cycle. We are seeing the economic accessibility to advanced node to economic accessibility to chiplet and 3D IC technology that was not accessible to the whole industry until now. Software is driving the workloads, driving the clever architecture that are now possible with these economic changes. And the EDA, these are all feeding this ecosystem. We are all trying to slow it down so that we can make money. In some cases, we need to stop and recognize that it's now is a swing where we are needed to think differently and invest more. Are we slowing down? We are being complacent about the technology that we introduced 10 or 15 years ago. I'm a UVM guy. We should have moved on from that to the next great thing. But that's not really the topic. The topic is now the topic is how we do recognize economic changes and innovation changes, and as the EDA and IP provider, how do we prepare the industry for what comes next? But we haven't been complacent. We have been investing the new stuff all along. I want to defend our industry. Have you reached the point that verification is ahead of complexity growing? No. But have that introduced new things continuously? Absolutely. When I did my first chip, we did eye verification, and then this little company in the Cambridge came with this pre-designed processor. We have invented IPLUs, things like IPU jack. We have invented UVM, but then we also did things like accelerate portable stimulus for system level verification, and there is so much innovation going on, which perhaps hasn't come out yet. We have invested in a test generation automation for verification. I would advance us a little bit, but yes, UVM, I hear you. I was on panels a long time ago discussing whether UVM goes from IP to system and all that. We have definitely innovated. Have we innovated fast enough? Alan, the survey says no. I see. The drop off in the first pass access rate was so dramatic that it can't just be about those few very leading edge designs that are having problems. Everybody must be having problems. Is this a sign of the other seismic problems within the industry of not having enough engineers? Companies can't find enough verification engineers. Do semiconductor companies expect more from an engineer now than they ever did in the past? Schmeister, can we question the survey first? We did our own survey, and what we see is not quite as bad, but the trend is definitely in that direction. We also have to ask where these failures are coming from. If you look in the list of them, the actual cause these issues, functional verification is still number one, but then you have maybe two other things. You have power, you have yield, you have performance, you have analog issues. You have a lot of things that cause a respin. Part of it is the first time right definition. You have a lot of things that cause a respin that are not same. When I switch it on, it doesn't work. You don't consider it because you don't meet performance, you don't meet power, and you need a respin to make it financially viable. Are you suggesting the requirement have tightened? Exactly. The requirement have become higher. The outcome of all this complexity is no longer binary like it was in the 90s, when it either worked or it didn't. And it's not that we didn't care about performance and things like that, but things were much simpler. Semiconductor companies have almost failed because the chip was correct, but they were able to convince the software guys to not use certain combination that would make the chip fail. The error is important. I've been joking in the past, saying I've actually seen a functionality correct chips. I've functionally correct chips within the context of the error, and of which there are many that define what not to do. There is a software hardware workaround. The requirement haven't heightened. We didn't innovate fast enough, and there's issues. But with all the things we do now, with agent designing things, and the agent now verifying things. The question is, which agent is faster and better? We need to really look at the heightening requirements around here. With the numbering requirement has increased exponentially, but so have the dimensions. Performance comes into play, power comes into play. We have all these dimensions you have dealt with now, so it is a multi-dimensional problem. If your workforce has not been scaling, you have an issue with your export. Before you would have a specialist, you would have a power guy, maybe a timing guy, or analog analog signal expert. You'd have these teams and swarm on these things. Now everything's independent, interdependent. Something could could go wrong over here. You fix it, but you destroyed something on the other side. That's hard to wrap your head around. It's easy not to have full coverage and the workload is scaling. So how do you deal with that? If workforce is scoring, then you can have a team of specialists working on your chip. You have to make each person more effective and a multi-dimensional design. That has not happened. We don't have technology. It's probably where we are going with the AI assistive engineering. Master. This is similar to the region why the American phone numbers have 7 numbers. It's what people can remember. It's not that we as people can't expand our minds that just verifying more larger scope. It's really about the cleverness of how the verification phases are set up. With an individual can be the expert in 5 different things, but you equip them with tools so they can be semi-specialist. Maybe with the AI-assisted engineer, they can get by versus having an army of 100 specialists. The gap has to be closed by automation. Okay, thank you for your time. I read this paper today, but we failed to keep up. Thank you for your time. See you next time.